Hi all. So till now we considered the bodies in which the variation of temperature within the body was negligible. It means the body remain nearly isothermal during a transient process, and essentially small bodies of highly thermal conductivity materials behave like that, behave as a lump body specifically. So this lecture we will try to look on the transient heat conduction, transient heat conduction in large plane walls, long cylinders. Large here means that only one dimension is of importance. Other two dimensions are very large as compared to that dimension in which the heat transfer is occurring. So we will consider only the one dimensional heat transfer problem. That is the meaning of large and long here and sphere. For long cylinders, it means that axial conduction is negligible and only radial heat transfer we are considering. And for sphere, right, with of course spatial effects. Spatial effect, it means the temperature will be a function of space also in this analysis, and of course time that we have looked previously. So again, to recapitulate previous or lumped analysis, is valid when a body is at a uniform temperature at different times. Let's say it is at initially at time t is equal to 0, it is a temperature Ti, and for some particular time T1 it is having some temperature T1, and like that when it is exposed to surrounding ambient, means every point in the body is having the same temperature at every instant, t equal to 0, t equal to 1, and t is equal to t2, and so on. So it means there is no variation of temperature with respect to location, and only variation is with respect to time. So such bodies are called lumped body. I have stated this previously also, and for that cases the Biot number is generally less than 0.1 to consider it to be a lumped body. Okay. Now for this analysis which we are going to now see now, for this the Biot number, this criteria fails. If this criteria fails, then we have to go for this analysis for which Biot number is greater than 0.1. Okay, so for this analysis the temperature will be a function of space and time, function of space as well as time. So to begin with this analysis, consider a plane wall of thickness, total thickness 2L, and also long cylinder and long sphere, long cylinder and sphere. But begin with to give you the flavor of this analysis, let's just consider the plane wall, large plane wall of thickness, total thickness 2L, and it is having symmetry around this vertical axis, right? So we are calling this as x equal to 0, and we are considering only the one dimensional case. So it means dimensions in all other coordinates are very large, right? Like in y as well as in z. So and this x equal to plus L, this x equal to minus L. Okay, so total thickness is 2L. So to solve, and suppose it is brought into the ambient of having heat transfer coefficient H and T infinity as the ambient free stream temperature. So it will going to cool if the body is at some temperature Ti, which is higher than T infinity. Okay, the body is going to cool. Suppose the body as a whole, means at every point in the body, is having the same temperature Ti initially, but when it comes into the contact with the surrounding fluid, it is going to release heat, right? So as we are considering one-dimensional case, one-dimensional heat transfer, and we assume that the body, this plane wall, has thermal conductivity as constant, so we can write this one-dimensional heat conduction equation for this case. Okay, and since the body is symmetric about x equal to 0 plane, the temperature profile will be symmetric about the x equal to 0 plane, considering there is no heat generation inside the body and both sides of the body is exposed to same fluid. Alright, so this will be a partial differential equations, which will be the governing equation for this case. This is a PD of order 2 in x dimensions and order 1 in time dimension. So we will be needing one initial condition and two spatial conditions, which is nothing but boundary conditions, to solve this problem. So in general, the initial condition is specified like this: at any x at time t is equal to 0, the temperature is Ti. And boundary condition, since the body is symmetric about the x equal to 0 plane, so temperature variation along that plane in the vertical direction is 0. Gradient of temperature is 0 at that particular location. And the second boundary condition will be x equal to plus L or minus L, both are same. So heat flux at x equal to L is balanced by the convection on that surface. Okay, and when we solve this problem by advanced mathematical techniques, we will reach to this solution in non-dimensional form: T at x and time minus T infinity upon Ti. T is the initial temperature of the body. All right, and this is the solution. If we solve this problem, you can look any classical heat transfer book like in Cropera to see how this derivation comes. And just if we look carefully this equation accounting for the spatial and time variation of the temperature, let's say this first term, exponential term, is having Fourier number in this. So in Fourier number is alpha t upon characteristic length square. So time variation is accounting in this first term, and the second term is having this non-dimensional spatial coordinate, which is nothing but x by L for this plane wall, right? So it means if this is the plane wall, let's say we are interested in finding temperature at this location, which is nothing but x location, and total length is L on one side, so x by L is the non-dimensional temperature. The second term, cosine term, is accounting for the or take care of the positional variance of positional variation of temperature. And what is this C? C is a coefficient which is dependent on the positive roots of this transcendental equation. This is a nonlinear equation, and we have to find the root for a particular Biot number. For a particular Biot number, we have to find the equation of this root of this equation. Okay, and and then we put this zeta n in this equation to get the coefficient of each term in this. Alright, so this is the infinite series term, but it is observed in the literature that if Fourier number is greater than 0.2, the infinite series solution can be approximated by only a single term solution. Because all other terms decays away, so only first term remains, and the solution reaches to only the first term. So that's it, that we call as a first term or one term solution of the transient heat conduction equation. All right, but the solution is, however, inconvenient and time consuming to evaluate, so we have to rely on tabular or graphical forms of this solution. All right, so this one term solution is plotted for some geometries in the literature, like for plane wall, long cylinder, and sphere is plotted in the literature. And to find the solutions graphically, we need to introduce ourselves with some dimensionless parameters. So for plane wall, if we want to find the temperature at any particular location x at time t, then what is the temperature at this location? So this is plotted in the literature as a non-dimensional temperature. So Tx T minus T infinity upon Ti minus T infinity, and this is non-dimensional temperature or dimensionless temperature. Next is dimensionless distance from the center, which is nothing but capital X or X star. In some books capital X, or in some books X star it is written. So this is nothing but X by L for plane wall. Similarly, the non-dimensional temperature for cylinder will look like R time R, and other terms are same. Ti is the initial temperature at each location, means every point in the one dimension. Ti. And for this cylinder, it will be small r by capital R, or R naught. R naught is the radius of this cylinder. Just for the sake of completeness, Ti is the initial temperature. At every point, the temperature will be the same inside the body. At time continues to move in forward direction, the surface which is exposed to the ambient, it will reduce the temperature quickly to infinity depending on the heat transfer coefficient outside, and the inside is still at the Ti temperature, that is initial temperature, but as the time marches forward, the center temperature reduces, and it goes to it comes in equilibrium with the ambient temperature, in which there will be no heat transfer, and inside it will be going out to the ambient. That is why temperature is reducing. Similarly for sphere, the same equation, and we are familiar with Biot numbers H L by K. Note that we are not using volume by surface area as the characteristic length here. For